Okay, so here is how we are going to do this. We are going to identify key points in the course of a titration and figure out how we'll calculate the pH at each one of those points. And throughout, I will be showing a visual to go along with what's happening, and I'll show that visual first, and then on that visual slide there will also be some notes about what's going on, but we won't write them down because then I'm going to come back to this slide here and I will write down the theory and whatever math is involved, and then we'll fill out the titration curve. So let's get started. So our journey begins with water. And of course, water's pH is 7, and I will denote the relative pH with dark or light blue. And now I'm going to put in our strong acid, HI, which we know will 100% dissociate into protons and I- spectator ions or ineffective bases, and I'm not going to bother to show them since they don't do anything. Of course, now that we've added all these protons into solution, our pH has gone way down. The pH is low, and we can calculate it the way we normally would for a strong acid. So let's write some notes. Point A, initial HI. So we haven't actually started the titration yet. We have added 0 volume of base. Just what is the pH before anything happens? Well, you calculate the pH as you would a strong acid. Calculate pH as you would a strong acid, which we learned how to do a while ago. We recall that HI will fully dissociate into protons and I-. We have 0.0500 of this to start with, concentration-wise, and we'll use that formal concentration symbol to indicate that we know that none of it remains intact, and we end up with 0.0500 molar of protons, which we just take the negative log of, and we get pH equals 1.301. 3 sig figs in the concentration, so 3 sig figs in the pH, remembering that only numbers to the right of the decimal point count after we take a log. So let's add that point to the titration curve. We have added 0 volume of base, and we have a pH of about 1.3, and we'll label this point A. Now, let's begin the titration. Let's say that we add 25 milliliters of strong base where only the hydroxide matters. Well, the two neutralize each other until one of them's gone. In this case, we still have more protons than hydroxides added, and so we have some protons left over. And we'll find that the pH does not change rapidly at the beginning of a titration curve. And we calculate the new pH after figuring out how the neutralization changed everything. So let's make some more notes. Point B. And we are halfway to our calculated equivalence volume. In other words, we are at 25.0 milliliters. And we're just going to figure out what happens from the neutralization reaction. Neutralization. And we should know this reaction. In fact, we already wrote it down over here, but we're going to write it down again for the sake of writing some notes and doing some math. So H plus, then leave some space, plus OH minus, yields H2O, which is not interesting. Calculate moles, or millimoles, because this is neutralization. Volumes are changing. We need to take that into account. 0.0500 molar times 100.0 milliliters will give me 5.00 millimoles. And then for the hydroxide, same deal, but our concentration 0.100. I'm going to stop writing units because you should just know what they are. And at this volume, we are adding 25.0 25.0 milliliters. Multiply those two together, and we get 2.50. I'll write the unit this time to stress we are millimoles. And then because the two react to completion, we know that one of them will run out, and that would be the hydroxide, since we have less of it, 2.50. And then over here, minus 2.50. We end with 2.50 millimoles of our H plus still left, and the hydroxide is gone. And now I'm going to erase this to make some room. But imagine that underneath that 2.50 millimoles of protons that you already wrote down, that we're going to write a downward arrow and just indicate that the next step is to divide this by the new volume, because we can't solve for pH with millimoles, we have to get back to molarity. So our new volume of solution is that original 100 milliliters we had plus the 25 from the base that we just added, 125.0 milliliters. And that gives us 0.0200 millimoles per milliliter, or molarity. And specifically, we're talking about H+. And so now we should know what to do. Negative log. And we get pH is equal to 1.699. 1.699. So let's add that to the titration curve. Over at 25.0 mils, our pH has climbed some, but not very much at all, which agrees with what was on the slide before, that the pH does not change rapidly at this point. But it has gone up, which makes sense because we have lost some protons. And so that's point B. Now we'll move on to our next major point, which is the equivalence point itself, where we've added just enough hydroxide that every mole of protons from our strong acid has been neutralized, and none of our strong base that we're titrating it with is left over either, because we have equal moles or millimoles of both species. So all we're left with is water, which of course has a neutral pH. So let's make some notes. Point C, which is the actual volume of equivalence, which we calculated earlier as being 50.0 milliliters. By definition, at this point we have equal moles of HI and NaOH, equal moles of HI and NaOH, which means that the protons and hydroxide ions from each of them completely neutralize to give a neutral solution. Completely neutralize to give a neutral solution. In other words, the pH equals 7. And you don't have to worry about sig figs when we're neutral. Just write 7 and that's fine. As far as I'm concerned, that's all you have to write, pH 7 at the equivalence point. You don't have to show any math, but just to be complete in our notes, what's happened is our H plus hydroxide reaction has gone to completion for both species, so both of these have gone to 0. And we're left with nothing but H2O. Now, of course, if we have water, that itself is going to provide some H plus and hydroxide ions. So we're not really at 0 of those two species. We're just saying that we have none left from the strong acid and strong base that were added to the water. But anyways, let's add that point to the curve. So at 50.0 milliliters, our pH has jumped quite a bit to neutral. And it is not a straight line from B to C. What happens is there's a curvature where it's a shallow rise becoming steeper, steeper, and steeper, and at the equivalence region, it just skyrockets. And so that's the equivalence point. Our last point of interest is what happens after this. And since we've been increasing by 25 mils at a time, let's just jump up to 75.0 milliliters. So we keep on adding hydroxide to our neutral solution, and there's no strong acid left to neutralize, so that hydroxide just drives the pH to very basic levels. And so now what we're going to do is calculate the pOH of this hydroxide solution, and from that find the pH. There's two ways to do this. There's the long way, which is just doing the neutralization math, and then there's the short way, which is what we're going to write down. But really quick on the slide, I'll show you what the long way looks like. We would just write out our neutralization reaction, figure out our millimoles as before. This time we have more hydroxide than our initial amount of protons, which makes sense because we're past the equivalence volume where those two values would be equal. So we run out of protons and we're left with 2.50 millimoles. We would then divide by the total volume of solution, which at this point is 175, find the molarity of hydroxide, negative log to find pOH, subtract from 14 to find pH. So how can we make this a little bit faster? Well, let's write that down. So point D, 3/2 of the equivalence point, 75.0 milliliters. Neutralization, but this time the hydroxide's in excess. But hydroxide in excess. The long way was on slide 21, but we're going to do the short way. So what we're going to do is take the concentration of NaOH, which we already know from the beginning of the problem, it's 0.100 moles per liter, or millimoles per milliliter, and we're going to multiply by the volume of hydroxide post-equivalence. In other words, we have added 75.0 milliliters total, and 50 of those milliliters went into reaching the equivalence point. And so there's really 25 milliliters of hydroxide solution just left over. And by multiplying these two values together, we will get the moles of hydroxide that are left over or in excess. And we will take those excess moles and divide by the new volume of solution. We'll call this volume solution total, which is just 175.0, the original 100 mils of acid plus the 75 of base that we've added. And so by taking the moles of hydroxide that we just have left over in solution, as we saw in that visual earlier, and dividing by the new volume of that solution, we will get the hydroxide concentration of this solution, which we can then easily find the pOH and pH from. So let's quickly do it. If we plug in the numbers correctly, we will get 0.0142 molarity of hydroxide ions floating in solution, negative log that. We get pOH equals 1.845. pOH equals 1.845. And then we just subtract that from 14, and we get pH is equal to 12.155. And so let's add that point to our curve. At 75 milliliters, we're a little bit above 12. And once again, we don't connect the dots with a straight line. We continue this sharp rise, and then it levels off and gradually rises to that high pH value. And so the equivalence point is at the steepest part of this sharp region here, and in this class we'll just estimate it as being right in the center of the sharp region, although in reality that's not always going to be the case. And so that is the titration curve. We could keep going to 100 milliliters, but we wouldn't learn anything new because we would just be adding more and more hydroxide to the solution, and we would just plug in new numbers here and get new final answers. The pH would gradually rise, but there'd be nothing interesting to see. And so to summarize everything we just went through, we have this slide, it's slide 22 in the PowerPoint. We covered how to calculate the pH before the titration began. Before we reached the equivalence point, we chose halfway to the equivalence point, but the math that we learned could be used anywhere before we reached the equivalence itself. Where there's no math to be done, pH is 7, it's neutral. And then after that volume, we do that excess hydroxide calculation. So lots of information in this video. Next we'll cover how we actually use this analytically.